Okay, dressing up y equals x squared. The graphs of all quadratic functions are related to the graph of the basic quadratic function y equals x squared. And this is actually kind of the basis of your success in this course and the next course, is just understanding of transformations, because the first chunk of 30-1 is transformations, and this is sort of your first intro to transformations, right? So you want to make sure that you got a handle on this and get this figured out, and then when you go into 30-1, it's going to be like, hey, we did that transformation stuff last year, and it's not so bad, right? And so we're starting with a basic function, y equals x squared, and we're going to do stuff to it, and we're going to see what happens when we change different parameters. And that will result in transformation. So this investigation examines the effects of three types of transformations. Multiplying x squared by a number, so if we get y equals 2x squared, or negative 5x squared, or 0.5x squared. Adding or subtracting a constant to the variable. So what if we go y equals x plus 4 quantity squared? So when I say quantity, it means that the x plus 4 is going to be in brackets, right? It's not. If I say x plus 4 squared, that's different from x plus 4 quantity squared, right? One would be x plus 16. And y equals x minus 7 quantity squared. And then adding or subtracting a constant term to the x squared terms. What happens if we add 6, subtract 1, etc.? And what happens if we put them all together? And it's very important that when we do transformations, that we do them in a specific order. Okay, so we're going to start today. You'll understand that order. You'll live by that, and when you get into 30-1, it all stays the same. So nothing changes. There's no sort of, oh yeah, but this does this, unless it's Wednesday and there's a full moon, in which case this happens. Okay, it's always this does this. Makes life a lot easier. And this is what we're leading up to. Y equals a, x minus p squared plus q. The general quadratic function, and we want to figure out, okay, so what happens when a, p, q, what happens when they change? All right, to do any of this, we need to become really familiar with the basic quadratic, y equals x squared. So we're going to complete the following table. These are going to be the key points we use all the time, and we're going to graph this. So I'm going to shrink it down a smidge. You can fill the table in. How's that? Maybe go a little bigger. Perfect. Okay, what's negative 3 squared? 9. Negative 2 squared. And then 1, and then 0, and then 1, and then 4, and then 9. Okay, now we want to graph that. So, let's use red. So I've got negative 3, 9. Negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, 3, 9. And then symmetry comes in here, right? I mean, if it's negative 3, 9, then it's positive 3, 9. Right? Our axis of symmetry is the vertical line, x equals 0, right? And then we draw this with a smooth curve. Okay? So when you're drawing parabolas, make sure it's a smooth curve. Don't V it. I'm just going to do this one branch at a time. And then we put an arrow on indicating, right? Whenever you draw a graph on paper, you should always put an arrow on to indicate, yeah, this keeps going forever in this direction. And there we go. That's your basic parabola, right? And what we're going to look at is, so what happens when we change? When we put a number in front, when we add or subtract something from x prior to squaring it, or when we add or subtract a number after it's been squared. So what I want you to look at is just some characteristics, right? And that is, from the vertex, for the basic quadratic function, when you move over 1 unit, how far up do you go? 1. When you move over 2 units, how far up do you go? 2. 4. When you go 3 units, you go 9, right? Which is what? So you move over 1, it's 1 squared, which is just 1. When you move over 2, it's 2 squared, right? And when you move over 3, it's 3 squared. So sometimes later on, given a graph, you can figure out the value of a just by saying, well, normally when I move over one, I move up one. But this time, this happened, therefore, well, right? So that's, by having this burned into your head, right, that it's, where the vertex is, because this thing could move, right? I mean, it doesn't have to be here. It could be up here and that, and then we'll look at it. Now, sometimes you might have to algebraically do it, and I'll show you ways, right? This is how you algebraically determine the value, but sometimes you can just look at it and say, oh, from this I know that. Okay. All right, basic quadratic function. So the shape of the graph is a parabola. The coordinates of the vertex are 0, 0. Hang on. And the equation of the axis of symmetry is x equals 0. Right? So we should plot that. Kind of hard to plot in on top of a huge black line. But. Okay, your basic parabola. So the effects of a on y equals ax squared. Demonstration. Here, watch. What we're going to do is this. This is the coolest thing. Ah, damn. Didn't want to do that. Hang on. Okay. Didn't want it. I wanted Google. Okay, this is called Desmos. D-E-S-M-O-S. Desmos.com. You can get it online, obviously, because that's where we are. It's an online graphing calculator. Now, there's nothing wrong with your graphing calculators, but there's a lot more with this that you can do, right? I mean, you get a nicer grid, blah, blah, blah. So if we're doing our investigations, all the stuff we're doing, you could do on your graphing calculator, but I think we could do it better here. Now, proviso is you have to know how to use your graphing calculator because that's what you're going to have with you on the exam. So, don't do everything on here and then you walk in an exam and say, oh, I don't know how to use this. It's available also as an app for iPhone or iPad or Android probably. I don't know, I don't do Android. So. Yeah, I'm an Apple fan. So. Okay, so let's go y equals ax squared. Now, it's going to say add slider. This is the cool part, right? Add slider a. Okay. So, I'm going to change the value of a, and you're going to look and see what happens, right? Now, before we do that, let's look at so you've got the questions in front of you. So, just changing the value of a, change the position of the vertex. So, you're going to look for that. In general, what effect does a have as the absolute value? Have you seen this before? Okay, so the absolute value of a. Absolute value just means the magnitude or size of a, right? So if a is -2, its size is 2. If a is 2, its size is 2. Okay, now we will be doing absolute value later on, so there, it's been defined for you. It just says take whatever's in between those bars, evaluate it if possible, and then make it positive. Okay, so it's negative, change it to positive. Okay, and then blah, blah, blah. Okay, so let's go change the value of a. And see what happens. Okay, so is the vertex changing? No. No. Oop. What happened there? Yeah. Oh, wait. Now a is negative, and what's it doing when a went negative? It's going down. Here, let's just do this. It's more cool. Just going to bounce back and forth between. So you can see it has 10, and then it goes down. It's going down to -10. And so we're just saying, well, right now you're looking at, so what happens for the shape as the a value gets bigger? What's it doing? It's getting narrower, right? It's getting narrower. So is the a value, and does it matter whether the a value is getting bigger negative or bigger positive? No, right? As the a value gets bigger, this thing is getting narrow. Okay, playtime's over. All right. So, does changing the value of a change the position of the vertex? No. In general, what effect does a have on the graph?
The width of the parabola.
Width of the parabola. Okay, sure. So, makes the graph narrower or wider. So you do that. Now in 3-1, we're going to change it. We're never going to say it gets narrower or wider. We're actually going to, because there's going to be more going on there. But for now, yeah, it's good. As the absolute value of A increases, what happens to the graph? It gets narrower. If the absolute value of A is greater than 1, then the graph of y equals ax squared is blank, then the graph of y equals x squared. All right, maybe we need to go back here. Oh, it's still playing. Stop. There. So let's make the, whoops. It's the width of the, no, it doesn't matter, I'm holding the pen, I can still point. Okay, so there's 1. Okay, now what does it want us to do? So it's greater than 1. Oh, so the absolute value is greater than 1, then the graph of y equals x squared. Oh, is what? So as I go greater than 1, then it gets narrower, right? Okay. So if the absolute value of A is greater than 1, so it doesn't matter if it's negative, right? In other words, like if it's 2 or negative 2, it's just going to be narrower than the graph. And we say we have a vertical stretch by a factor of the absolute value of A. Okay, so here, let's pop back. Let's set A to 2. There's 2. Okay, so it's, and here, let's just graph y equals x squared so we have a reference. Okay, so there's y equals x squared, is the green, and there's y equals 2x squared, which is the red, and it's narrower. Okay, flat. So if we go over 1, you got to watch scale on this thing, right? It's like I'm going, but I'm going over 1, or it's, no, that's not 1, that's a half. So if I go over 1, then the normal graph goes how far? Up 1. Go over 2, it goes up 4. Okay. So now I go over 1, and this has gone up how much? 2. And if I go over 2, normally it's up 4, but now it's up 8, because we have said, okay, if we go to our operations, right, you're going to square the x first, and then what? Then you're going to double it, right? You can multiply it by 2. Okay, so what we say is that what's happening is that we're getting a vertical stretch. So this point, 2, 4, is being stretched up, right? So it becomes the point 2a, 8. Okay. So although it does get narrower, right? Physically, you're looking at it getting narrower. What's happening really is it's being vertically stretched by a factor of 2, right? So we're taking every y value, normal y value, we're doubling it. So what was the point 1, 1 becomes 1, 2. 2, 2, 4 becomes 2, 8. 3, 9 becomes that. I have to play with it, so I'm not going to do that. Okay, now so we say we have a vertical stretch by a factor of A. That's how we're going to describe it, right? So you see an A value, you say that this graph is vertically stretched by a factor of A. Okay, or the absolute value of A, right? So even if it's negative 2, you say it's vertically stretched by a factor of 2. If the absolute value of A is less than 1, so in other words, like 1/2 or something, okay, so let's do that. I'm going to change that to 0.5. Or not. 0.5. Okay, and move this back a bit. Okay, so remember the green is the, so 1, 1, but now we've got 1 and 0.5, right? You watch scale. So normal point is 2, 4, but now it's 2, 2, right? So we've taken half of it. So we say the graph gets wider, but what we really want to say is that it's vertically stretched by a factor of 1/2. right? So it's vertically stretched by a factor of a, regardless, right? That way, life is consistent. You just say it's a vertical stretch by a factor of a. Doesn't matter if a is bigger than 1 or smaller than 1. Okay, so blah, blah, blah. The graph is wider. Okay, so it gets wider. So physically, that's what you're seeing. And we say we have a vertical stretch by a factor of absolute value of a. Yeah. Isn't life wonderful? If you ignore narrower and wider, you just say, hey, it's vertical stretch by the absolute value of a. When a is positive, the parabola opens. When a is negative, the parabola opens down, right? That's why we separate the sign out, right? We say, I don't care if it's positive or negative. That's telling me the direction of opening. Once I've dealt with that, then I can tell you that, oh, and it's a vertical stretch by a factor of whatever the number is, whether the number was positive or negative. On your calculator, graph y equals x squared, negative x squared, 3x squared, and negative 3x squared. Okay, so you could do that, right? And on the color ones, it actually wouldn't be bad, right? Because you'd see 4 different graphs in 4 different colors, and on the other one you see. Okay, so hang on, let me just. Okay, what do we want? Y equals x squared. What else? What were the other ones? Y equals negative x squared, negative x squared, and 3x squared and negative 3x squared, right? Okay, there they are. And let's there we go. Take it back. Centering the grid. Okay, now it's asking some questions, right? What are the questions? And you see the different colors. So this is like a color, you know, TI-84, only bigger and fancier. So green is x squared, and then we've got negative x squared, which is blue, and then we've got black, which is 3x squared, and we've got red, which is negative 3x squared. How do the graphs of ax squared and negative ax squared compare? Reflected where? Reflected on the x-axis. So it's a reflection on the x-axis. So the graph which is a negative, so they are reflections of each other. On the x-axis. Reflection. The graphs of y equals x squared, y equals 3x squared, y equals 0.4x squared, and 5x squared, as well as the graphs of 2 other functions are shown below. Label each one with its equation. Okay, well, how are we going to tell what's what?
X squared would go 1 to 1 and 2 to 4.
Okay, 1 to 1. So this guy must be y equals x squared then, right? Okay. So then, what's this guy? The innermost. 0.4. So do we get narrower as we go higher or wider?
As you go higher, you can narrow.
So we go narrower as we get higher. So the narrowest graph must be 5x squared. Now to check that, we're going to have to go over 1, because remember it said there's 2 other functions. So we're going to go over 1 and up 5. Yeah, that looks right. Okay, so this guy is y equals 5x squared. Okay, so what's the next less narrower one? So 1, 2, 3. So that's 3x squared. Okay, that's why. So what's this guy? We've got 1 and yeah, it could be 0.4, eh? That's probably 0.4. Especially because the other 2 open down and none of those are negative. So okay, so this is y equals 0.4x squared. Okay. So really, we didn't even have to count it, right? If those are the four graphs and they're the ones opening up, then the narrowest one has the largest value of A, and then as we go outwards, we're going to get smaller values of A. So we've done that. Write the equations of the other two parabolas. Okay, so how are we going to do that? What's this guy? Negative 3x squared, right? Okay, so we know it's negative because it opens down, and we know it's 3 because you go over 1, hey, we went down 3. Okay, so this one is you go over 1 and you go down, I don't know, it's tough to figure, probably 0.4 again, right? So it's a reflection of the other one. So y equals negative 0.4x squared. Okay, so now we've dealt with stretches and reflections. That's what A does, right? It's a stretch by the absolute value of A. And we just ignore the sign. And then we look at the sign and we say, oh, so it opens up or it opens down. Compare the points on the graphs y equals x squared, 1/2 x squared, 3x squared with an x coordinate of 1. What do you notice about the y coordinates of these points? Okay, so we probably don't need to graph them, right? We can figure this out. So if x equals 1, well, so we could just plug it in, right? So if x equals 1, y is equal to 1 squared, which is 1. Y is equal to 1/2 of 1 squared, which is 1/2. And y is equal to 3 times 1 squared, which is 3. So if x is 1, then these guys are what? They're A, right? So if x is equal to 1, then the y value equal to A. Which we already said in so many ways, right? We already figured that one out. Oh, hey, it's not. In y equals ax squared. Okay. Good, we're a quarter of the way there. All right, everybody good? The effect of p on y equals x minus p squared. Okay, so we're just going to go to here, and we're going to kill all these guys. And I'm going to write y equals bracket x minus p, y equals x minus p squared. And I'm going to say add a slider for p. Okay, so p is equal to 1. This is y equals x minus 1 squared, right? So remember, when this is positive, you're looking at x minus that p. Okay, wait, go away. Okay. Oh, so what's happening? Vertex is changing, so what's it doing? It's moving along the x-axis. Which way? Both ways. Somebody say left or right. It's going left or right. Okay. So is the shape changing? No. So the vertex changes, the shape doesn't change. It moves to the left or to the right. So when p is positive, which means you're looking at stuff like x minus 2 squared, which way did it move? Stop. Okay, so here, p is positive here. So here we've got x minus 2. So which way did it move? To the right, how much? 2. Yeah, I'm saying 2, but I'm 1.9, but whatever. Okay, 2. When it's 4, it moves 4. Okay, when it's negative 2, which way did it go? Left. What does this become? X minus negative 2. How would I probably say that? X plus 2. So when it's x minus, it moved, and when it's x plus, it moved which is just totally wrong, right? It's backwards. But that's how you got to remember it. I don't know. You got to figure this out. How do I remember this?
Negative, it's negative, it's
Yeah. So this moves which way?
right.
How much?
Forward. Nothing. And upright.
Right 4. Left 2. We already did that, didn't we? Okay. Anyways, so there's the graph, right? But we saw it live. We saw them move. So are the graphs congruent? That is, do they all have the same size and shape? Yes. If P does not affect the shape and the size of the graph, what effect does P have on the graph? It's not just the vertex, right? It's not like that one little point just separated itself and moved, right? It's the whole, yeah. So the graph, you know, or the curve, let's see. So the graph translates. Use the fancy word, right? So we've got vertical stretch as one of your transformations, and the next one is a translation. So it translates left or right. P units. Okay. No absolute value of P here, right? It's translate left or right P units. State the vertex of each of the functions in the table shown. So, regular old y equals x squared vertex is 0, 0. This guy, the vertex is
0,
4, because it moved 4 to the right. And this guy, the vertex is 0, negative 2. Okay, everybody got that down? It's a plus, it moves left. It's a minus, it moves right.
Wait, is it the x value that's front or is it the y value that's
What do you think? What's it always been?
the x value?
Yeah, it
So
still
shouldn't
is.
that be 4, 0 then?
No.
Because the x
Yeah.
value
Because it moves on the x-axis.
Oh, sorry, you're right. Do it. I shall leave that up, YouTube. I have been corrected. That's why you guys are here. Make sure that it at least comes out right. Yep, you're right. Thank you. Let's do the vertex. Complete the following statements. All right, let's see if I get this right. The graph of y equals x minus 7 squared is the graph of y equals x squared translated horizontally 7 units to the right. The coordinates of the vertex are, okay, somebody say it, because I'll get it. 7, 0. The graph of y equals x plus 5 quantity squared is the graph of y equals x squared translated horizontally 5 units to the left. The coordinates of the vertex are negative 5, 0. So when you're describing a translation, I want to see or read the following, right? Horizontally translated 7 units to the right, or to the right 7 units. I don't care which way you say it, right? It doesn't matter. But they must include both pieces of information. Which way and how much, or how much and which way. Okay, you need both of those. You can't just say it was translated 5 units. Yeah.
On our
Okay.
it says British.
Is it really?
Yeah.
Seriously? Sure you're not on like 3 or something? Oh yeah, it does say.
Yeah, I am. Yeah.
Yeah, you're on part D.
Never mind.
Never mind. Left. Go left. Go left. We're on the left side of the page. Okay. Well, number 2 reads differently here. Parameter P. What do you say for number 2? Does it say parameter P or does it say in the equation? Yeah. Okay. So there may be slight differences between. This is from 2013. Okay. In the equation y equals x minus p quantity squared. Parameter P, oh, there's the parameter P, translates the parabola horizontally, absolute value of P units relative to the the graph of y equals x squared. If P is a positive value, the equation will look like this, y equals x minus P, and the graph is translated to the right, And if p is a negative value, it'll be translated to the left. That's the only other choice. So. The coordinates of the vertex are p comma 0. So that's nice, right? It just means whatever follows a negative sign, that's p, right? So if it's x minus p, well, first of all, you know it goes right, and so you know that it has to be a positive. And if it's x plus p, then you know it goes left, and then it has to be a negative. State the equation. Isn't state wonderful, right? Like you don't have to show any work. Okay, equation A, what's the equation? Y equals x plus 4 quantity squared. Okay, you do B and C, right? And then look up. So don't look up until you've done B and C. Oh, wait. Do I change? No, I'm sorry. Okay. Good? Any questions? Did I mess up yet again? Sometimes I'll make mistakes on purpose. Most of the time they aren't. But sometimes I will. And when I do, then, I want to be corrected, which means that you'll also correct me when I make them not on purpose, which will happen often enough. So this guy's saying thing, right? But the negative in front says what? Well, you reflect it in the x-axis, so it opens down instead of up. The effect of q, now vertical, on y equals x squared plus q. Okay, so let's do something here. So I want the x squared plus q. I'm going to add a slider for q. I'm going to take out the slider for p. It's 1. What happened to it when it was 1? Where's it going? 4? Down. Up or down? Here, press play. Let's go up to 10 of the window. It's kind of out of the window. But now we'll see it when it goes down to 10. That's kind of cool. How many x-intercepts?
1.
Really? How many x-intercepts?
None.
None? How many x-intercepts now? 1, and then 2. Yeah, okay. Right, I was typing. That's a little off. So if it opens up and it's moved up, how many x-intercepts? 2. Okay. It opens up and it's moved up, how many x-intercepts? 0. Okay. Right. The graphs of y equals x squared plus 3. Now notice, we square the x, then we add the 3, right? With the x minus p, right, if you have x minus 2 squared, you subtract 2 from your x value, which really has the effect of moving it to the right 2 units, right? And then you square that. Okay. That's why it moves right when you subtract. So if you take away 2, put a 2 in there, 2 minus 2 is 0, it moved it over to 0. Anyways, are the graphs congruent? They all have the same size and shape? Yes. If Q does not affect the shape, then what effect does Q have? So Q does what? Translates vertically. So vertical translation. Up or down. Q units. So that's the formal, right? Here's your formal stuff. Stretched by a vertical stretch by a factor of, reflected in the x-axis, horizontally translated 3 units to the right, vertical translation up 5 units. Okay. Now again, I don't care. When you're talking translations now, you have to distinguish. Is it a horizontal translation or a vertical translation? Feel free to use HT and VT, right, as abbreviations, right? So you're not, So if you write something like HT, right, 3, I'm cool. You write HT up 4, not so cool, right? But if you write VT 5, not so cool. VT up 5 or VT 5 units up, cool, right? So translation, what kind of translation? Which way? How much? Reflections, just a reflection in the x-axis, vertical stretch by a factor of, and then you state by a factor of what? State the vertex of each function. All right, let's see if I can get this one right. 0, 0. 3. That's in the right place now. And negative 5, right? Okay, so Q seems to do what it says it's going to do. It's okay, nobody's surprised. Q seems to do what it says it's going to do. The problem is we're like 3 days a week right there. Q says it's going to do, Q does what it says it's going to do. If it's positive, it moves up. If it's negative, it moves down, right? P, on the other hand, well, okay. Complete the following statements. The graph y equals x squared is translated vertically, how many? Which way? The coordinates of the vertex are? Graph y is blah, blah, blah is translated vertically. Okay? When we talk about P and Q, we're just using really the absolute value of them, right? We don't care if they're negative. We're saying it moves 5 units to the, then if it's negative, P it moves to the right. If it's positive, it moves to the left. With Q, if it's negative 10, it's moving 10 units down. Now, when we go to write the vertex, then that has the effect, right? In the equation, parameter P translates blah, blah, blah. If Q is a positive value, then the graph is translated. And if it's negative, it goes. And so why is this blank bigger than this blank? The coordinates of the vertex are 0, comma, Q. Ah, so what are the real coordinates of the vertex? P, comma, Q. Right? When there's a P and a Q, vertex will be a PQ. Because now, well, okay, wait. First, we have to state these equations. So go ahead, state the equations, write them down, and then look up. And I'm going to make one mistake, at least one mistake. One will be on purpose. Okay, so what needs changing up here? Yes?
The negative x squared.
Negative x squared. Okay, cool. Everybody got that? Stuff's easy, isn't it? Really? Good setup for 30-1 now. You're going to just breeze through that first unit.
You wouldn't need a bracket for any of those, right?
No brackets.
No brackets.
No brackets. Yeah, so putting it all together. All right. Suppose you want to sketch the graph of y equals negative 2, x plus 3 quantity squared plus 4. How do you handle all three of these transformations? First, you have to determine the effect of each of the numbers. Okay, now, translations are done in a specific order. And it's the same way, the order when you get out of bed, right? So the first thing you do is you stretch. And then you walk to the mirror, and then there's a reflection. And then the analogy breaks down unless you come to Spanish or French and start translating things, but translations are last. And the translations doesn't matter if you do horizontal, then vertical, or vertical, then horizontal. But you must do your stretches first, then your reflections, then your translations. So, what's the transformation the 2 made? So we're going to say it formally, right? It is a vertical stretch by a factor of 2. What does the negative sign do?
Makes a
Reflection. What about it? In the x-axis. Do you think you could also reflect in the y-axis? Not till next year. But next year you can reflect in the y-axis. Not this year. Okay, we do reflection in the x-axis.
Isn't it already a reflection in the y-axis? So it should be symmetrical.
Yeah, unless you move it first and then do it. You can do transformations out of order, but you would be told to do them out of order. Right? So you'd be told, hey, translate this, then reflect on the y-axis. That's a different ultimate equation. And yeah, parabolas are symmetrical about the y-axis, so it wouldn't matter. Describe the transformation the +3 made. Okay, so horizontal translation. I'm going to write it out in big words, but in future, if we're in a little box trying to fill stuff in, you could write HT. So horizontal translation, 3 units to the right.
No, it'd be to the left.
Yeah, it's to the left.
Okay. I was relying on you guys that time. Okay, and describe transformation the +4 made. Vertical translation. Okay, and you could have said translation left 3 units or whatever it was, and you could have said up 4 units. Okay, so it doesn't matter. But you got to say what transformation. It's a horizontal or vertical. It's what translation. Horizontal or vertical, which way, how much. We will graph this in 4 steps. First, plot the key points of y = x squared. Okay, I'm going to shrink this. 125 seemed to work, right? Okay, and where are we here? So we have, what, 4 graphs here, right? Okay. So first plot the key point. All right, so 0, 0, go over 1, up 1, go over 2, up 4, go over 3, up 9. Right. So that's how I graph a parabola, right? Just go over 1, up 1, over 2, and then go 1 this way, but it's still up, right? Because we're squaring. And it's symmetrical. Okay. So that's what we're starting with. Keep that in mind, right? That's our starting point. Next, we sketch the graph of y = 2x squared. The effect of the 2 is to vertically stretch the graph of y = x squared by a factor of 2. To graph y = 2x squared, we need to multiply the y-coordinate of each key point by 2. Okay, so it's going to be 1, 2, and 2, 8. And 1, which should have been 1, and 2, 4, so. Okay, so far so good? So the resulting parabola is what? Narrower. You won't use those words in 30. But that's okay. Here we can use those words. Narrower and wider. Next, we sketch the graph of y = -2x squared. The effect of the negative sign is to reflect the graph in the x-axis. The graph of y = -2x squared. To graph that, we need to change the sign of the y values. Okay, so 0, 0, right? I mean, what's happened to it's still on 0, 0, right? So a vertical stretch has no effect on the vertex. A reflection has no effect on the vertex. Okay, so now 1, but now we're at -2, and 2, and we are at -8. We'll answer it or something. Or send it to voicemail. Okay, so the resulting parabola now opens down. Okay, so stretched it first, became narrower. Now we reflect it, so now it opens down, and now what's next? Finally, graph this. We translate the graph 3 units to the left and 4 units up. So what I'm going to do is take each point. Okay, and I'm going to move it to the left 3. So the point 0, 0 goes to 3 left, and then 1, 2, 3, 4 up. The point which was at, I'm going to go from the left here. So the point that was at -1, 2, right down here, goes 3 left, 1, 2, 3, 1, 2, 3, 4. And the point that was at -2, 8 goes 1, 2, 3, 1, 2, 3, 4. And the point that was at 1, 2 here goes 1, 2, 3, 1, 2, 3, 4. And the point that was at 2, 8, sorry, 2, negative 8 goes 1, 2, 3, 1, 2, 3, 4. Okay, and we've done that right. It should be symmetrical about this new axis of symmetry, right? And then we sketch. Not very well. There we go. So there's our final graph. Now, we could plot the journey of each of these points as they went through the, so the vertex did what? Well, it got stretched by a factor of 2, but it's 0, 0, and 2 times 0 is 0. Then the y value got made negative, so it's still 0, 0. Then it moved 3 units to the left, so it went from 0 to negative 3, and 4 units up, so that went from 0 to 4. So 0, 0 ended up at negative 3, 4. Right? Now 0, 0 is kind of a boring journey for one of them, right? So let's say we examine 1, 1. So 1, 1 became 1, 2. Became 1, negative 2. Became, so I got to go 3 left, so this will be negative 2 and up 4, so it became negative 2, 2, negative 2, 2. Okay. So you could, I mean, if you want to do it in one fell swoop, I mean, you could just take each point and apply all the transformations to that point and say, okay, where does it end up? Okay, I'm not going to go into huge detail on the rest. Practice, practice, practice. That must be for you to do. Reach and fly. Well, or maybe that, I don't know, is that for you? Or I'll tell you what, you do it, I'll put the answers up here. If you disagree with any of them, check with a neighbor. If both of you disagree, let me know. Maybe I messed up. But I do have a key here. I'm hoping it might actually be right. So, take a look at these guys. What I'm going to do is basically, I'm just going to pause it because, there's no... And there are the answers. So, I'll leave that up for like 2 seconds. You can always, if you're watching the video, you can pause it at this point, right? For each of the following, describe the transformations. State the coordinates of the vertex. Use your knowledge transformation to actually draw the graph on the grid without a graph calculator. So here's the thing, right? We don't need a graphing calculator. Oh my god. We don't need a graphing calculator. And we're back. Okay, so the new parabola. Vertically stretching by a factor of?
3.
Resulting in a parabola that is? I hate that one. Reflecting the resulting graph in the? Translating the resulting graph.
Right form up 5.
So it opens down. Let's see, it opens down. Resulting in the x-axis. Yeah, reflecting the resulting. Yeah, reflecting in the x-axis. Yeah, okay. So it opens down. So I'm going to say what? HT right 4 and VT which way? Out 5. Okay, cool. What's the vertex? What's the vertex here? Negative 6, 1. What's the vertex here? Negative 3, 2. What's the vertex here? 0, 0. Phew. What's the vertex here? Perfect. And what's that there for? All right, let's just do this. In summary, you can fill in the rest of that table, right? I mean, it's kind of. In summary, the graph will have a vertical stretch of
A. What? It's not A.
Absolute A. Oh.
the absolute value of A. will open up if A, and will open down if has a vertex at and has a vertical axis of symmetry with an equation of equation. What's the equation? X equals P. Don't forget that. Not good enough to put a P. Okay, so here's what I'm going to do. I'm going to do this. They wanted them graphs, so I'm just gonna, I'm lazy. Okay, so vertical stretch by a factor of 2, horizontal translation left 6, vertical translation up 1. What do we got? We've got reflection and x-axis. So in order, right? There is no stretch, right? No number in front there, so there's no stretch, no A. Well, there's not no A. What's A?
And do 1.
1. Okay, if A is 0, you just don't have a quadratic anymore, right? So reflect in the x-axis. HT, left 3, BT, 2. I tend to prefer direction and then how much over how much, but you can say it's 3 left, doesn't matter. What do we got? Yes, 3. That's it. I mean, we could say narrower, I guess. I just don't like to. Narrower. Wider. Okay. Cool. And I'm guessing on here we're probably supposed to graph them all.
Yeah.
Okay. Well, A, B, C, D, E. I don't wanna. All right. So, yeah, well, I'm not going to do it while I'm recording. So I'll graph them and then you can look at them. And if you're watching the recording, then here are the answers.
Oh.
And I'm going to stop recording now. So you might want to pause if you want to continue to stare at this. But we are done.